about the objective meta theory of simplified order calculus.
Thanks, Carlo. So as a bit of background on this talk, I previously gave a 2-hour version at Johns Hopkins, and I made the very bold decision of giving every single mathematics definition in AGDA. This was not a popular choice. I have since remade my slides, and they're now words, many words. But one thing that I think this loses the emphasis of is that this is a mathematics talk, but it's also a formalization talk. The main idea is, how do we do categorical logic on a computer, right? And so the structures that I'm presenting, I think, are a maximally efficient ergonomic way to put categorical logic on a computer. But what's the goal? Anyway, so I'd like to start off with a story. I was teaching 2 summers ago a course on type theory. It was like a very ambitious course. The students started off by learning how to prove things. It was introduction to proofs. Then they learned how to program in rackets. Then they learned how to implement their own proof assistants.
Is that okay?
Actually have it off? I would,
Sure.
yeah. Because slides, there's blue like in yours. Just the off button, yeah. Good. Anyway, so at one point I was looking at the source material and there's the definition of substitution. And I found a mistake in it. And I'm like, aha, okay, so I'm presenting the correct definition of substitution. Then one day later, I'm in the bath and I realize there's another mistake. And so I have to issue a correction. I'm issuing it in class, and then a student asks, is there any way that we can know that our definition is correct? And I say that the notion of the correctness of a definition is very tenuous. So you can try and go to sleep at night thinking that you have the correct definition, but you can really never know. And there's another issue that comes around. Suppose you ask me what is simply type lambda calculus, and I start giving you a presentation, and I have to make some choices. Am I going to use names, or am I going to use de Bruijn indices? Am I going to use explicit substitution, which adds a term constructor for substitution, which then you add rules for how to propagate it? Or am I just going to use direct substitution and not bother with that? And so with all of these differences, you get languages that are slightly differently behaved, you get different reduction rules. And the question is, are these all the same language? What connects all of them? So do I even know what simply type lambda calculus is, much less can I know that I've implemented it correctly? And surprisingly, I was wrong. There is a resolution to these questions. And the resolution comes from Lambda in the 1980s, although it had been known for about 10 years prior to this. I asked Audi before for a reference. And you can give a one sentence definition of STLC. And you can say STLC is a freely generated contextual Cartesian closed category. Now, there are words in that sentence, and you can explain what all of those words mean, but suppose you explain to a computer what those words mean. Then you can construct such an instance, and you can prove that it has the required universal property. And these words don't refer to substitution, they don't refer to reduction rules. So assuming that you know how to define category correctly, and you can look at your definition and say that's correct, then once you've actually implemented substitution and creating an instance of these, you actually know that there are no bugs in your substitution. And that's a very amazing idea. And so the main point of this talk is to explain this concept of categorical logic, how you actually are able to specify an entire programming language with a lot of intricacies in a single sentence, and also how one would actually put this on a computer. And so with that, I'm going to begin with a few data structures. So we're going to be working in an ambience type theory, and we are going to implement a type theory in the type theory. So we have some type tie of types. Oh, this is going to be a typical ambiguity in reuse of type theoretic language in the object and meta theory. But sure, if we have a notion of types, then we have a notion of contexts. What are contexts? Contexts are just lists of types. So here I give 2 constructors. It's going to be an inductive type. There is an empty context, and given a context and a type, I can extend. Now, let's suppose that I have some notion of elements. These aren't terms yet, they're just going to be some family parameterized by types. So if I have some notion of elements for every type, then I can get some notion of indexed lists. I get a family that's indexed by contexts. So starting with a family that's indexed by types, I get a family that's indexed by context. How do I build this? Well, it's just a list, except it keeps track of the types of all of the elements. So you can start off with the empty list, which is indexed by the empty context. and then given an index list of elements sigma, and given some elements t of type A, you get an index list sigma O plus t of index by context gamma plus A. So this is just an index list constructor, and that description is pretty helpful. Now, finally, elements don't look like terms. What will I mean by a notion of terms? A notion of terms is anything that's indexed by a context and a type. And using my index list constructor, I can create a notion of substitutions, which is going to be this T of S plural construction. So starting with a family that's indexed by a context and a type, I get a family that's indexed by two contexts just by querying the argument gamma downstairs. And so anything that is of the form of TM, in other words, indexed by a context and a type, will be a notion of terms. And elements of this type TMS will be known as substitutions. Now, another thing that we need is variables. So if we have lists, we can ask, well, is there a certain type in a context, right? And these are going to be intrinsically typed de Bruijn variables. There's going to be a zero variable, which says that A is a type in context gamma plus A. And if we have a variable showing that A is a type in gamma, then we can also show that A is type in context gamma plus B by applying the successor variable construction. Now, these look, you may say, well, these behave like indices. We're just indexing into a type. The really surprising thing is that intrinsically typed de Bruijn variables are not actually as well behaved as you'd expect. So one expectation that you might have is that these would be a subtype of the finite ordinals of size, length, gamma, right? So there are just some indices that work. Well, what actually turns out is that if you look at the first constructor, A appears twice. And the zero variable construction actually looks like the Ruffle constructor of a marking law of equality type. So in general, variables will be a set only if types are a one type. But then you might have multiple proofs that the last variable is there. So if your types are a set, then you'd actually get a subtype of fine N. So that's a surprising thing that I found about intrinsically typed de Bruijn variables later on in the formalization. Now, the cool thing about variables is that they index a type in a context. So yeah, if we have an index list that's indexed by a context, then we can pull out a specific element from it as per that indexing thing. And this function I'll call derive. So derive, given elements of type gamma and given a proof that A is in gamma, you get an element of type A. Now, finally, variables, they're indexed by a context and a type. So they look like some notion of terms. Well, what do I get when I take them as my notion of terms? In this theory, then, these substitutions are known as renamings. So renamings are just substitutions made out of variables. And we can actually show that there's a category structure on renamings. So first off, if there's a variable and then there's a renaming, then I can sort of substitute into the variable just by picking out a specific components of that renaming. If we look at the types, I start off with a proof that A is a type in delta, and then I have a renaming from gamma to delta. And so I get a proof that A is a type in gamma by picking out the according variable, because somewhere in sigma, there has to be that proof. And similarly, we get a way of actually composing two renamings just by mapping this substitution function onto each component of sigma. Now, similarly, we can get the identity, and we do it with this game. What we do is we first define weakening 1 and weakening 2. Weakening 1 takes a renaming from gamma to delta to a renaming gamma plus A to delta, so it weakens the domain of the renaming. And we just do this by mapping the successor variable onto each of the variables in a substitution sigma. And then weakening 2, now the codomain has an extra A inside of it. And how we accomplish that is just by throwing in a zero variable. Now, how do we get identities? Well, we can start off with the empty substitution and then just repeatedly apply weakening 2 to it. And we get a renaming from gamma to gamma. Now, this looks like a category, but it's not just any category. It's a category of a very special form. Sort of substitution, composition of substitutions is not a primitive notion. A more primitive notion is this substituting into a variable. And so it's a category where the objects are made out of types and the morphisms are made out of terms. And we'd like to make that structure precise. And that's going to be captured in the structure of a simple contextual category. Oh, and I forgot to mention, of course, we prove left and right identity laws and associativity, so we can get all of the structure necessary. So here I come to the definition, and this is the definition that I'm most proud of in my formalization of the meta-theory of STLC. This really simplified a lot of the formalization. I'm going to define what a simple contextual category is. And this is going to describe the class of models of simple type theory. So simple type theory is type theory without type dependency. And my claim is if you have a simple type theory, it is of this form. So you start off with some type of types, a notion of types. And as a consequence, you get a derived notion of context using the list former that we had from before. The next thing that you need is some notion of terms. These are indexed by a context and a type. Once you have a notion of terms using the index list former, you get a notion of substitutions. And I'm going to denote these by TMS, lowercase. Next off, we're going to start with a notion of substitution. The terminology is slightly overloaded. So there are substitutions and then there is substitution. And what substitution does is it takes a term and it takes a substitution and it substitutes the substitution into the term. And from this, we get a notion of composition of substitutions by mapping a substitution into each term. And finally, we are going to need an identity substitution. Any questions? Okay. Now, all of this data is going to be subject to some laws. So we have the identity, so we can stipulate left and right identity laws. Notice that these are the first 2 points above. There's actually an asymmetry between these two statements. The first statement involves composition, while the next one involves substitution. But from the statement involving substitution, we can derive a similar statement from involving composition by mapping that statement or by using that proof in every component of the statement. Similarly, we can stipulate associativity. And associativity is stated in terms of substitution as opposed to composition, but we can derive a statement in terms of composition of substitutions by, again, applying it in every component. And finally, needed technical assumption, as with the definition of distinction between a pre-category and a category, we're going to want Hom sets. And we're going to stipulate that we have Hom sets by specifying that each of the term sets is an H set. And from this, we can derive that each of the substitution sets is an H set. So what does this definition say? Morally, this definition looks very much like the definition of a category, right? Except for the fact that the objects are made out of types and the morphisms are made out of terms. Well, we can start playing around with this definition. So we have an identity substitution. The identity substitution is, in particular, an index list of components. So what can we do with a list? Well, if it's non-empty, we can take first and rest of it. So given a context gamma plus A, the generic non-empty context, we can take first and rest of the list to get pi and z, the fundamental context projection and the zero variable. We can define weakening by substituting in the fundamental context projection. So now we have a notion of weakening in any contextual category. And similarly, we can prove a statement that's like one of the identity laws that we saw before, but in terms of weakening now. And it's a statement for how substitution acts on a weakened term. And I'm going to explain the significance of this when we get to the notion of variables. So we have a theory of weakening. That's cool. It's cool that all of our structures have this, but weakening isn't cool. What's cooler is variables. So in particular, we can actually index each of the components of the identity using our variable data structure from before. So we're going to let var denote variables with our notion of types. And then given some variable, we are going to index the components of the identity. So make var v refers to that particular component of the identity indexed by that variable. One of the cool things that we're able to show is basically like one of the identity laws for variables. How does substituting into a variable work? Well, it just picks out a component of that substitution. Then we can prove some more things. We can prove, for example, a relation about how a successor variable relates to a variable. If you make a successor variable, it's the same as weakening the making of the variable. And using this, you're able to prove a functoriality law. So remember that renamings had this categorical structure. So if we're working in the category of renamings and we consider a substitution inside of there, and that gives us a variable and we make it, then that's the same as making the variable and making the renaming, which is just indexing each of the components in sigma. And so this is a functoriality law. This says that their structure of renamings, when we embed renamings into our contextual category, that embedding is structure preserving. And the other functoriality law is actually much simpler. All that it says is that if you tear apart the components of an identity and you put them back together, then you get back to the identity. So these two together, what they say is that there is an internal contextual pre-category of renamings. And the reason that I say pre-category is because, remember, variables are not going to be a set in general. And from this internal contextual pre-category, there is a contextual structure preserving functor from there to your to the contextual category in question. So in other words, the theory of variables, everything that you can do with them is interpretable in any contextual category. So every contextual category has a theory of variables. Now, finally, we're able to explain the asymmetry between the left and right identity laws that we saw before. We could, instead of founding the theory with identities, have just instead stipulated that we give each of the variables. Then the the law that would involve composition would now be the law that we see here, which does not involve composition, which just involves substitution. And then the asymmetry disappears. And similarly, identically, we could have founded the entire theory using a notion of weakening. So there are three equivalence presentations of the theory, and this presentation with variables actually recovers a traditional definition of a Cartesian multi-category. So what I discovered was that Cartesian multi-categories are an excellent class of models for simple type theory. Now, finally, sure, so any simple type theory has a structure of a simple contextual category. Now, what does it mean for a simple contextual category to have function types, let's say? And what Lambda discovered is that this comes with the notion of Cartesian closed categories. So we're going to give a definition, not for categories, but for simple contextual categories of what it means to be Cartesian closed. Now, what this structure involves is, first off, there has to be an arrow operation on types in the theory. So for every two types A, B, we get an arrow type, A arrow B. Then for every term in context that's extended by A, we can abstract over A to form a term of the arrow type. So our usual lambda. And then there are two equivalent choices that we could make. I'm going to choose to postulate the more programmatical application operator, which given a term of arrow type and given a term of the domain type, gives us an application term of the codomain type. Now, category theorists will prefer to work with the categorical operator, which looks like an inverse to lambda. And that can be derived with the formula that appears here. Now, we're going to need to specify some structure, and there are exactly three laws that we need. We need naturality of lambda. And here I'm using a weakening 2, which I haven't defined before. Weakening 1 can act on substitutions, and then you add a 0 variable at the end and you get weakening 2. Okay, so lambda is natural. And then we have our beta and eta laws. the beta law could be stated as simply as the eta law with inverses in the opposite direction, but we prefer to make the statement about the programmatical app operator. In one sense, because maybe when we prove that our normalization by evaluation algorithm is correct, and we produce something like a computational trace, we'd like it to be in terms of the operations that we're familiar with in the structure of our programming language. Now, so finally, I'm going to wrap up. And the question is, so then what is simply typed lambda calculus? Well, we have simple contextual categories, and we know what it means for such a thing to be Cartesian closed. We will call these contextual CCCs. Now, we also can define in a pretty straightforward way what it means to have a functor between two contextual categories. So this is known as a contextual functor. And then we can ask, what does it mean for a contextual functor to preserve CCC structures? So these definitions are pretty direct. There's not that much interesting about them. Now, finally, we need to get started somewhere. If we, in lambda calculus, we can't just have arrow types. We need to have some base types. And going back to that statement of simply typed lambda calculus is a freely generated contextual CCC, freely generated by what? So in this case, I'm just going to consider freely generated by one object. If we consider freely generated by one object, then we're working in the category of pointed contextual CCCs. And then the morphisms are base point preserving, CCC preserving contextual functors. Then what is an implementation of simply typed lambda calculus? It's nothing but an initial object of this category. So finally, what did I do in my STLC project? I proved that every implementation of the STLC, according to this notion, has a normalization theorem. And that proof was done purely in terms of the universal property. So my code base proves normalization, and only after that does it construct a model of simply typed lambda calculus. And in order to actually construct a model of simply typed lambda calculus, and in order to have equalities between terms in traditional presentations, I had to use cubical agda so that I could have a hit model. And in particular, so what is a normalization theorem in this sense? Well, one of the things that it implies is decidable equality for terms. So if you ask what is a normalization theorem, if I do not have a series of reduction rules, and I can't say that normalization means that every sequence of reductions terminates, well, one of the ways is it gives decidable equality, and that gets you to like 90% of what the meaning of a normalization theorem is. And so that's the end of my talk. And also, I can't help but mention that this is my 1-year HRT anniversary, which is considered a pretty major occasion. Thank you.
Questions? First of all, so one thing that I thought was very nice is that the point you made at the end, you don't need to construct the initial model of lambda calculus in order to show that it has normalization.
Mm-hmm.
Instead, you just say anything that has the correct universal property has this great property. So that's really cool and maybe nice for people who have experienced suffering and working in these.
Oh, and of course, I should mention at this point that the formalization is based off of a 1995 paper by Thorsten Altenkirk. Thorsten and collaborators, Hoffman and one other person. Yes, there we go. They went on actually a series of papers that basically did objective proofs of, and the term objective is actually coined by John. So it turns out that there is objective metatheory and subjective metatheory. So who knew that a math theorem could be subjective? But in the Altenkirk's proof, his paper basically adapts to an objective proof, although it is not strictly speaking an objective proof. So it's just small tweaks because all the categorical constants is there, you do get an objective proof.
So I had another question though. So another possible definition for what is the simply typed lambda calculus is that it's the initial Cartesian closed category. forget context.
Mhm.
And prove all the same results that you proved in that language too. And it seems that morphisms between models of the Lambda calculus very rarely strictly preserve the grading of the contextual category. So I would like to better understand what role the contexts play in your take on the objection and theory of Lambda calculus.
So I think that the answer is, I'm surprised to hear that morphisms usually don't preserve the grading of context. That's
Usually
interesting.
morphisms don't preserve choices of arrangement, usually.
Sure.
Product or product.
Right. The main thing is ergonomics of implementation. That's actually my primary concern here. And again, it sort of disappeared when I removed the AGDA code. But when you saw the AGDA code, you can see that this is a pretty direct and ergonomic thing.
Thank you.
So, done a lot of writing of solvers for various equational theories in AGDA. I'm wondering how we can somehow extend this result, like very simple equational theories, and somehow use that to derive some sort of normal or decidable equality of terms for other very simple equational theories. Trying to get solvers like that for free, or not for free, but in this style. So, do you think that's realistic? Or
So, I mean, as soon as you add things, very quickly the categorical logic interpretations disappear. If we're doing, but that's not even the entire story. So if we're doing dependence MLTT, we know that it's locally Cartesian closed categories. But then did like Thorsten et al. Actually get to a proof of objective proof for that? They didn't. Later, though, Thorsten and Capozzi wrote a paper on that, maybe 25 years after the original papers. And very quickly, even if you have the actual categorical logic, which you don't always have, getting the objective normalization proof, well, perhaps you need a bunch of John's machinery for that.
okay.
Yep.
Oh, sorry. Okay, so in your definition of contextual category, the terms form the set, but not the types.
Right. And you can actually ask in the formalization if this is necessary. And it's because when I construct simply typed lambda calculus, and I have, for example, insert beta and eta laws explicitly, and then I need to interpret those into a model, I use is set is square p to handle some of the higher coherences. Now, here's the catch. Suppose that I prove normalization, and then I construct an initial model that is not actually a hit model. It's a model where I have normal forms representing the terms, and I have no relations. This requires a normalization theorem to do. In that case, I think that I wouldn't actually run into situations where I have this. And I think that I could construct an initial model without the truncatedness assumption with the use of a normalization theorem. And you can sort of do the project twice to bootstrap it. So it's not like a fundamental circularity obstacle. And so I think that it might actually be worthwhile to consider semantics without the truncatedness assumption entirely.
Right, I would kind of expect to have the types truncated.
Now, there is a
types.
very unfortunate thing in my proof for the initial model. I need the initial model to have decidable equality of types. The reason is because I need to eliminate, and I eliminate into these twisted gluings. Twisted gluings have pre-sheaves in particular, and they're pre-sheaves of normal forms. But pre-sheaves of normal forms, basically in having variables, they embed the structure of types, and so I would not actually get pre-sheaves.
Yeah.
So I wouldn't, the normalization argument does not go through. So I technically, it's not 100% objective. I only prove it for initial models that actually have decidable type equality.
But you should be able to prove that the initial thing has a set of objects, without assuming it.
Yes, because all initial things are isomorphic. And in particular, so if I can construct one initial thing in which that holds, I can carry it over.
And you definitely don't want to assume in general that a contextual CCC has a set of objects. Like for instance, the category of sets doesn't.
Yeah. And this is sort of like usually even in the Hawk book, when we consider category theories have Halm sets, but they don't have sets of objects necessarily.
Right. But
Steve, did you have a question?
Like, I don't know, natural models of CWX or so on, then you usually have this assumption, so like, then the category set is not an example of those, which is kind of weird.
I would say it's not a good formalization.
Yeah. Anyway.
I was just curious how similar your proof is to isn't Fiore the one who usually is credited with the normalization for the simply typed lambda calculus? We were looking at that proof around here last year. And worked on that.
Was it a formalization though? Was it a formalized proof?
No, but you said you have a normalization proof for your contextual.
Yes. So
Blah, blah, blah.
my proof is derived almost entirely, almost verbatim from Altenkirk's 1995 paper, which is titled a reduction-free.
Yeah, that's the only what I have.
No, a categorical reconstruction of a reduction-free normalization proof. That's the title. So I mentioned that to John in the comments. And so the proof is not original.
And that's Altenkirch, Hoffmann, and Streicher.
Yeah.
Maybe I make one comment about the relationship between the Altenkirch
You know, okay, great.
and the Fiore from 2002. So there is a need in each case to close the types under this thing invented by Bill Tate, which is that you have a map from the neutrals into the computable elements, and map back into the forms. And the main difference between the two proofs, aside from the fact that Marcello's argument is more categorical than the Altenkirch-Streicher argument, is that Altenkirch, Hoffmann, and Streicher build that closure structure of normals, neutrals, and so on into the definition of the category of the group category. So it's not a conventional ruling, but some kind of not standard ruling. What Fiore does is he uses a standard ruling along some node, but then he proves by induction that all the types have this closure structure. So I'd say that's the main difference in the proofs.
And I think that I also want to mention that Altenkirk et al. Went on to give an objective proof for system F. But that was an unpublished draft. And it looks like they use an impredicative type theory. So that might be hard to formalize because of that reason. But like after I finish my PhD, the project that I want to work on is this formalization for system F.